The first type of statistical test that we'll have an opportunity to explore is called the one sample t-test. Now, as we investigate this type of statistic, we need to keep three assumptions in mind, and here they are. The first is that the data must be continuous. In other words, there must be some kind of numerical value associated with our data. Secondly, the data must be normally distributed. In other words, if we were to take the data that we're going to assess, and if we were to plot it on, let's say, a bar graph, we should see that our data fits under what we call a normal distribution curve. And you may be familiar with that term and what that looks like if you've taken other math-related courses. Thirdly, the sample must be conducted randomly. In other words, if the sample was conducted purposively, it would not fit or it would not be fitting for us to use the one sample t-test. The purpose of this statistical measure is to provide the researcher an opportunity to compare the mean of a sample with that of a population. So let's jump into an example so that we can see how to conduct this type of statistical measure. Here's our scenario. We have discovered that the mean age of 100,000 people in the county is 60 years old. We then decide to see how this information compares to a sample of 100 people from our local city. From our research, we have discovered that the mean age is 64 and the standard deviation is 6. Is there statistically significant evidence to prove that these values are not the same? So the first thing that we want to do anytime we're presented with a scenario like this is we really want to pull out the numbers of interest. So let's look at the first. The mean age of 100,000 people in the county is 60 years old. And so again, this data represents our population because we're looking at the county, which is a much larger population, if you will. And so the next pair or the next set of data is related to our sample, which is coming from 100 people in our local city. So again, our county is representing the population and our local city is representing the sample. Now in our sample, the mean age is 64 and the standard deviation is 6. And so you're probably familiar with this, but when we talk about a standard deviation of 6, what we're saying is that the mean age of individuals in our city is 64 plus 6 years of age, or 64 minus 6 years of age. Here's the question. Is there statistically significant evidence to prove that these values are not the same? What we're saying through all of this is there a difference between 60 years of age and 64 years of age? And so if I were to ask you now, is there much of a difference between these values? You may say yes, and you may say no. But the beauty of this is that we can use the power of statistics to help us determine whether or not there is a statistically significant difference between these averages. So here's how we do it. We use something that we call the 7-step hypothesis testing format. Here are the steps we'll investigate. First, we have to state our hypothesis. We then will need to set our alpha level. We'll then move on to step 3, which is to compute the test statistic. Number 4 is to determine the degrees of freedom. Number 5 is to identify the critical value and the rejection region. And then number 6 is to state our statistical conclusion. And then number 7 is to state our clinical conclusion. All right, so we know that we're looking at a comparison of our sample and our population. We know that our sample has 100 people. The mean average or the mean age is 64 years old, and our standard deviation is 6. Now, for our population, we have 100,000 people, and we know that the mean age or the mean average is 60 years old. So again, the question that we're focusing on is there really a difference between these values, 64 and 60? So the question that leads us in this 7-step hypothesis testing format is our sample mean statistically different from the population mean? All right, so let's jump into the very first step of our hypothesis testing format. The first step is to state the hypothesis. And so as we state the hypothesis, we need to see, first and foremost, that we're going to have two things that we need to list. The first symbol that you see, which is listed as H subscript 0, is equal to 0, is technically referred to as H naught is equal to 0. That's the way that we refer to it in statistics. So here's the first one. Our null hypothesis would say that there is no difference between the sample mean, our city, which is 64 years old, and the population mean, which is 60 years old. Again, our null hypothesis doesn't necessarily represent what we believe to be true. Again, we only use this for statistical purposes. So again, we have the phrase in here that there is no difference. And so if our null hypothesis says no difference, then we have to ask ourselves, what then would our alternative hypothesis say? And our alternative hypothesis would then say that there is a difference between the sample mean, 64 years of age for our city, and 60 years of age for our county population. So here we have it. We have kind of both ends of the spectrum. We're saying that there's possibly no difference and that there's possibly a difference. Here's our second step. And our second step for this will always be the same. So hopefully you remember that our significance level, or our alpha level, is always going to be 0.05. And what this really means for us is that we're establishing a 95% confidence in our results. And so if we give ourselves 95% confidence in our results, that means that we're also giving ourselves 5% chance of making an error. So the way that we list this in notation form is we use the Greek letter alpha in lowercase form equals 0.05. Our third step involves what we call computing the test statistic. And our third test will always be some type of formula that we need to solve for. So first, as you write down this particular formula, let's identify exactly what each of these letters and symbols mean. The T here represents the test statistic. Okay, that's all that means. It's all that it represents. And so when we talk about the T test, we're finding, or we're solving for this value called T. Next, we have X bar, and you're probably familiar with this. The X bar usually means or refers to an average, and it does here. This is going to be our sample mean, or our sample average. And this Greek letter mu in lowercase form here, this represents our population mean. Okay, so again, we've got the test statistic, we've got the sample mean, and we have the population mean. Now, in our denominator here, the S is going to represent what we call the standard deviation. And then we have this square root symbol, and under that is a lowercase n. And the lowercase n here is going to represent the number of people that we have in our sample. So now that you know what each of these letters and symbols represent, take a moment here to see if you can pause the video and determine for yourself what our test statistic will be. So taking our formula, which is noted here at the top, and plugging in the values into this formula, which is noted here at the bottom, we should have T equals 64 minus 60 over 6 divided by the square root of 100. So if we have that, we're on the right track. Now the next screen that you'll see will show how we break down this formula to get our T value. So what we see is that T then equals 4 over 6 divided by 10 which gives us 4 divided by 0.6, which ultimately will give us a t-value of 6.67. Now for step 4, we have to determine the degrees of freedom. And this is a very simple formula, and what this is going to help us do is determine one of the values that we'll need here in the next few steps, which is to find our critical value. And it's hard for us, or maybe impossible for us, to find our critical value without first determining the degrees of freedom. So here's our formula. Our formula here is df, which stands for degrees of freedom, we'll see that here momentarily, equals n minus 1. So again, df is our degrees of freedom, equals n minus 1. And n here is simply going to represent the number of people that we have in our sample. So if you remember, we had 100 people in our sample. So 100 minus 1, of course, gives us 99. So we're also going to hang on to this value as well. Now, here's what you'll need to do. Feel free to grab out a critical value of t table if you have it. If not, I'll put one here on the screen so that you can look at, but I think it'll be helpful if you do this yourself. But we need to look at this critical values of t table to help us find our critical value. So here's a sample table of the critical value of t. Now, one of the first things that we need to do is locate our 0.05. Remember, we said that our alpha level is 0.05. Again, we're giving ourselves 95% chance for confidence to say that we're correct, and we're giving ourselves about a 5% chance to have made some type of error. So we have this box highlighted that represents our 0.05. And then notice on our degrees of freedom column here on the far left, we have the numbers 40, 60, 120, and the double zeros here would represent infinity. And so remember, from our fourth step, our degrees of freedom value was 99. And so what we're going to do is we're going to go up to the next highest value, and we're going to find the critical value that's associated with our 0.05. So that value for us would be 1.980, or just simply 1.98. So again, we need to hang on to this value as well. So let's move on to step 5. Step 5 has us to identify the critical value and the rejection region. So keep in mind, we just found our critical value just a moment ago, and we said that our critical value is 1.98. And so what we're going to do is we're going to put that on both sides of the graph that we've created. So on the far left side, we're going to list this as negative 1.98. And on the far right side, we're going to list this as positive 1.98. What this does is help us to determine whether or not we should reject the null hypothesis or fail to reject the null hypothesis. Any value that falls on our two endpoints here, any value that is greater than 1.98 or any value that is greater than negative 1.98 falls within our rejection region. And if that value falls within our rejection region, we are then going to reject the null hypothesis. So we now need to ask ourselves where our t value resides. Remember, our t value from our third step is 6.67. So if I ask, where does that value fall? You would be correct if you said it's going to fall over here on the right hand side, because 6.67 is definitely greater than 1.98. And so we can show that here in our graph. So we're almost there. Let's look at steps 6 and 7. All right, step 6 calls for us to make what's called a statistical conclusion. And for this step, all we simply need to do is really recount what we've just shown in our graph. So we would say here, our observed test statistic falls within the rejection region. Therefore, we reject the null hypothesis. So let's think about that for a second. What we're saying is that our t-value fell in the rejection region, and because it fell in the rejection region, of course, we're rejecting the null hypothesis. And remember that our null hypothesis statement says that there is no difference between the sample mean and the population mean. So if we reject that statement, we have to ask ourselves, what are we really saying? So if we reject the fact that there is no difference, we're essentially saying that there is a difference between the observed sample mean, which was 64, and the population mean of 60. So here's what we'll say for our step 7, which is to make a clinical conclusion. For our clinical conclusion, we're going to say this. We're going to say that we have statistically significant evidence to show that the sample mean of 64 is not the same as the population mean of 60 years old. So let's talk about this for just a second. Anytime we reject the null hypothesis, we are saying that we have statistically significant evidence to do so. So if you would, maybe jot that down somewhere. I'll give it to you again. Anytime we reject the null hypothesis, we are saying that we have statistically significant evidence. Okay? So again, for this particular problem, we have statistically significant evidence to show that the sample mean of 64 is not the same as the population mean of 60 years old. Practically speaking, there's a difference between the age of those who are in the city and those who are in the county. So I hope this was helpful. If you feel comfortable with where we are, please take a moment and complete the sample problem that's associated with our one sample t-test. Thank you.